Okay, so good to go from my side, I think. And welcome back, guys. Let's see if some more people join or join online. Okay, one it seems. Let's briefly recap where we left off. There was a tiny bit left in last unit, in the unit from last week, about advanced techniques for fixed parameter tractability. We talked at length about LPs last time and how to use those for stronger kernels. And then the flip side was how can we get lower bounds for problems where we do have FPT algorithms, but we don't know how far we can push the running time of the f of k part. And so we were looking at some tricks there, or some techniques. That was basically the summary here. And it was based on this hypothesis from complexity theory called the exponential time hypothesis, which basically says if I want to solve a 3-sat problem, I want to decide whether a given 3-sat formula is satisfiable, I really have to pay exponential time for this, not just non-polynomial, as would come out of p not equals np, but really exponential. And we discussed a bit that there's, in principle, creativity for growth of functions is limitless. There's a lot between polynomial and exponential. So the what we'll use today is basically always the same idea. We'll do some kind of reduction, but it's not as it's not a clean carp reduction in that sense. I guess it's more akin to a Turing reduction. We try to say, suppose that this exponential time hypothesis is false, or suppose we have some algorithm that solves a problem that we want to show is hard, then we can also find an algorithm that would contradict this exponential time hypothesis. But the statement here is deliberately vague. It doesn't say how this algorithm explicitly looks like. In particular, it will not be like a usual carp reduction where we take an input and produce one output, and then that's what we run this alleged algorithm on. And it will need many calls to this algorithm for the problem. Okay. What we discussed last time is that the exponential time hypothesis talks about the number of variables in this formula. So it's a 3-sat formula of some arbitrary size, but the relevant parameter for the exponential time here is the number of variables. And we've seen many reductions of the type for problems where we care about showing stronger, well, lower bounds beyond just W1 hardness. These reductions tend not to give us this kind of bound. Like in this example of vertex cover, the size of the vertex cover is specifically the parameter for the vertex cover instance we generate depends on the size of the formula, the entire length, and not just the number of variables, at least not in a natural way. And it seems tricky to come up with better reductions in general. And the last bit where we stopped last time was this really obscurely looking sparsification lemma for formulas. And indeed, it's one of those results that are very, very tailor-made for one specific purpose, but it's also a little bit magical that it actually is true. And again, just to repeat that, it says there is, oh, it's a lovely quantified statement, but really it says there's a 3-sat formula that's given of a certain length and a certain number of variables, and we can output an equivalent formula that has the same truth value, where now that's a big disjunction, so it's a big OR of a big AND of small ORs. And each of these formulas in the disjunction is very nice in the sense that it's small. It uses the same k variables, but a bounded number of clauses in terms of k. But we have a lot of those formulas, okay? And then the parameters are such that you can first decide for essentially how many formulas you'd like to have. And then the constant k tells you how big you have to make each of the parts. And also you can compute such an equivalent formula in essentially the time it takes to output it. And again, we didn't do the proof. It was a bit lengthy and technical, so we'll just take this as a black box. Where we left off last time was using the sparsification lemma for 3-sat formulas to do anything interesting with it. And the first kind of step here that really shows you why this lemma is so useful is that we can transfer this bound from the exponential time hypothesis to one that involves the size of the formula, not just the number of variables. So a statement formally is, unless this exponential time hypothesis is wrong, there is some constant so that every algorithm for this parameterized 3-sat problem needs time exponential in n and k, the length of the formula and the number of variables. And so let's prove that. It'll be a proof by contradiction if you want. So we assume that such an algorithm exists, but the point is we have to get the quantifiers right. So there's an algorithm, but it has a parameter c, which is related to these constants. And so the statement says there is a constant such that this holds. If we want to use a proof by contradiction, we have to take the negation of that. So we have to say something about for all c. And assume that for all c, AC is an algorithm that solves the satisfiability problem. This should be 3-sat in the given time. So, well, if you state it as an upper bound, there's the exponential part as in here, but we'll probably need some polynomial part that we don't actually care about. That can be generous, but it should only depend on the size of the formula, not the number of variables, and it's a polynomial. I guess here n, the size, the number of clauses is equated with the length of the formula, because the formula is a 3-sat formula. That's a constant factor difference. So that's our assumption. Now suppose we're given some delta greater 0. And we want to show that there's some algorithm that depends on this delta that now solves the 3-sat problem in the time that would contradict the exponential time hypothesis. So B with delta. And so here we only have the exponential part for the number of variables. So if that was true, it would contradict the exponential time hypothesis. because this is true for any arbitrary delta. So there can't be, like the exponential time hypothesis claims, there can't be such a constant where this is no longer possible if I can find, for any arbitrary small constant, an algorithm that still does it in that time. That's the contradiction that we want to arrive at. And I guess it's technically not a contradiction because we don't know whether ETH is true, but it would refute this exponential time hypothesis that people believe somewhat strongly is true. Okay. How do we construct this algorithm B delta? One more parameter, just because it's more convenient, is delta half. Let's call that epsilon. And that's what we use the sparsification lemma with. So we take the sparsification lemma, invoke it with delta half. So the first thing is we get some constant k from the lemma. There's an epsilon. For every epsilon that we give it, there's a constant k. And we could write that this is a function of epsilon, but it doesn't matter. It's so that's the constant there. Now the sparsification lemma gives us what? It tells us we can rewrite our given 3-sat formula in this specific way as a disjunction with all the properties here. Maybe so that I don't have to go back all the time. Let me copy that part. So the first step that our algorithm B delta is, it invokes the algorithm that's behind the sparsification lemma, right? It's a constructive argument. You can construct from our given input, the formula phi. We construct the equivalent formula big disjunction of psi I from 1 to t, using the code from the sparsification lemma again. And then we have these properties. So, okay, I should say with our epsilon, delta half, that's the first step. Maybe let's say step 1. Now I want to decide my original formula. I know this one's equivalent, so I'm just going to try to satisfy this equivalent formula instead. Now this is a big disjunction. If any of the psi I is satisfiable, the whole thing is satisfied. So we call our assumed algorithm for each of the psi i's. I just have to tell you what this constant c is. And I mean, again, this is the way I'm presenting the proof is the final result of what you do. Normally, you would just leave that and work out backwards what the constant should be. It turns out it works if you set it to delta over 2 times k plus 1. It's capital K from the sparsification lemma. And obviously, if any of those is satisfiable, then we return true. If all of them are unsatisfiable, we return false. And I mean, this is what our algorithm AC tells you. It's a satisfiability algorithm. So what we still have to do is analyze the running time of the overall algorithm B delta that we constructed here. The first step was calling the sparsification lemma, and there we just have to peek at in the small print. The time is 2 to the epsilon k n to the c. I guess here the c is an arbitrary polynomial part, so let me rename it to c prime because c for us has a specific meaning. Okay. Now we can plug in what we know for epsilon is delta half. Okay, and the polynomial part. That's the first step. The second step, and by the way, this is looking good because it's essentially the running time we try to achieve. So remember, the goal is to show that we can solve P3 set in this time, 2 to the delta k and a polynomial. And here we have essentially that. The key part is it only depends on k, right? Not on the size of the formula. Now for step 2, we have a lot of these calls, namely as many as we have. So t times as many as we have size. I didn't copy it here, but the number of formulas is at most 2 to the epsilon k. Okay. And the time for each call on psi I is the time for AC. And so that was by assumption this lovely term. So 2 to the, just doesn't fit. 2 to the c times n plus k, and then a polynomial factor. That was this bit. Now we have to plug in what our c was, which is this. So we have the 2 to the epsilon k from the t. Then we have 2 to the this thing, delta divided 2 k plus 1, and then n plus k. But I should say here n is a different n. This n is, maybe we can call it ni or so. It's the ni is the size of the formula psi I. That's what we call this algorithm on. We don't call it on the original formula. We call it on each of these little clauses. Well, disjunctive clauses. I don't know. The little formulas psi I. And that's the last bit where we need the sparsification lemma. Again, going back up one more time. The number of clauses is bounded by capital K times K. Okay. Capital K times small k. And if you plug that in, so ni is less or equal big K. So here we have capital K plus 1 times K. So that just cancels with the K plus 1 here. So this one cancels with the K plus 1, and I have a factor K that I have to pull out And I could have plugged in what epsilon is here straight away. That's a bit nicer then. And you see we can simplify this to n to the delta k, sorry, 2 n to the b. And if you add up the two steps, the second is actually dominating everything, but the overall time is of this form. We can be generous and just take the delta times k and take the product of the polynomials, doesn't matter. But this is indeed this kind of time. I guess I should not have the same b here, so let's say b prime. The point is it needs to be some polynomial. Okay, so we've constructed an algorithm b delta that somehow solves the problem in using our assumption. It solves the 3 satisfiability problem in a time that contradicts the exponential time hypothesis. So if we believe in that hypothesis, we should refute our assumption. And that means we can't have an algorithm that even has this sub-exponential running time, because for every c, in the size of the formula. It doesn't work for the variables, it doesn't work for the size of the formula. That's what the sparsification lemma gives us. Okay? So this was the key proof technique. Now, we didn't maybe not care so much about 3SAT itself. We wanted to say something about vertex cover. But virtually the same argument goes through if you take vertex cover and use what we've just shown in a way. So you can take the same template. And maybe to make this explicit, let's really copy things as much as possible. We assume we can solve our problem, but this time here it's vertex cover. In this time. And this is in the time claimed in the statement. So again, the negation of needing exponential time would be something like times a polynomial in n. So you make that assumption. From that, we build an algorithm that solves a problem that seems to contradict. And we can take the shortcut to the previous theorem. So this time we work towards using this one. So again, the template was, suppose there's an arbitrary delta given, or I guess yeah. From that, suppose we can construct an algorithm b delta that solves oh, come on. Oh. And this time we're only aiming for delta times n, the size of the formula. And from the previous theorem, we know this would already contradict the exponential time hypothesis. And so here, this is actually much easier. This time we're given a formula, and we construct the vertex cover instance using the standard reduction from this picture. So we just take the normal, I mean, I don't know what normal means here, but the most standard reduction from 3-set to vertex cover just works. You can take it exactly as it's given here. So we construct a graph and a threshold. Using this reduction, and just to make it visual, there's this triangle for each clause. Oh, come on. There's this triangle for each clause, and there's these magic green edges between some of the literals that are negated. So you know what that means, and this is doable in polynomial time. And let me just use our assumed algorithm on this. And we can use delta divided 2, I guess. So here, the question is, what is the parameter that pops out? And here the parameter is 2 times n. If I start with the formula of size n, n clauses, then I have to check for vertex covers of size 2 times n. So this 2 comes from this reduction. And if you use other problems, you have to adjust this choice of this parameter c. But yeah, here it's relatively simple. Now clearly A solves this problem correctly, and it does this in the assumed time. The first step is actually polynomial time, though the overall algorithm solves your 3-sat problem in this time. And if you plug in what k is, then you get a 3-sat algorithm in this time. And that's, well, it means the ETH is false, and then you can make of that whatever you want. Strictly speaking, here is just copying. Then I'm inserting what we know about C and about K. And then that's exactly the claim here. Okay. So that's is one technique how you can get to some statements that the existence of certain algorithms is unlikely. It seems in this case specifically unlikely that you can substantially push further the exponential time algorithms for vertex cover. You can maybe push the constant of the exponential growth a bit further, but not all the way down to something sub-exponential in k. You can show similar results for other problems. And here I'm sparing you the proof, but because we discussed this problem in some detail, maybe you're curious just to know the result. For closest string, we had the essential growth of our algorithm was k to the k. This was the kind of depth bounded search algorithm that naturally pops out of the problem. And my point is, it's a very simple algorithm. And this statement says up to maybe a constant, well, it's still exponential improvement, but the key growth of algorithms solving this problem seem to require this k to the k component. So for this specific problem, closest strings is unlikely that we can improve the simple algorithm that we've seen by much. So maybe it's not worth looking. Okay. A quick wrap up of this unit. We've seen LPs as a versatile tool last week, and we've mostly used it for a better kernel of our vertex cover problem. And then on the negative side, we've seen these reductions from the exponential time hypothesis, which really the proofs become very simple as soon as you have the sparsification lemma. With that key tool, the rest is a twist on standard reductions. And so I think it's useful to know about this because oftentimes you have a problem where you can relatively easily argue that a certain growth for your FPT part is inevitable. But there's this magic step in between, the sparsification lemma. That also concludes the overall part on fixed parameter tractability. I had a slide for this, but I think I didn't copy the slide deck. All the slide would have said is fixed parameter tractability is great, but it still often leaves us with an exponential time algorithm or worse. Unless this parameter is really small, it may not solve our problem. The main uses for fixed parameter tractability is identify which problems are hard because of what. So there's it gives a more fine-grained picture. It's a kind of an adaptive analysis, and maybe you're lucky and your problem is actually not hard in the sense that your instances are hard, just in the worst case overall in inputs of size n. But if you have if the best algorithms you know about still run too slowly, it doesn't really help us further. If the problem with the type of inputs we have is still too slow, we have to compromise further if we want to get things faster. And so that's what we'll pivot to next. But before we go there, of course, any questions on this part, or also other parts about fixed parameter tractability might make sense now as opposed to after the next part. Maybe it's a good time for the break as well. Any burning questions? Ja.
Und zwar habe ich vor ein paar Tagen irgendwo was gesehen, dass irgendein Prof von MIT anscheinend vor ein paar Monaten einen richtigen Brecher bewiesen hat, dass man anscheinend ein starkes Resultat hat, dass man weitaus mehr Platz sparen kann für weniger Algorithmen, als man dachte. Dass man quasi sehr stark Platz für Zeit eintauschen kann.
Okay.
Also
In welche Richtung? Also man kann Platz sparen. So.
Ich glaube, das Setting war exakt, dass in einer Tapering Machine, dass wenn es Zeit t ursprünglich läuft, man es so simulieren kann, dass man maximal Wurzel t an Platz braucht. Also ich glaube, der hieß irgendwie.
Weil irgendwo muss es einen Haken geben, weil man könnte das ja iterieren, nicht? Man könnte ja die gleiche Konstruktion immer wieder anwenden, bis das Ding einfach gar keinen Platz mehr braucht. Ja. Irgendwo wird geschummelt an der Stelle, wenn man das tun würde. Wahrscheinlich braucht man immer mehr Zustände und immer mehr Zeit, aber trotzdem unklar. Ja, das bekannte Name natürlich, aber ja, bekanntes Paar sogar bei am MIT.
Scott Erickson hatte, glaube ich, auf Twitter das irgendwie gesagt, dass das irgendwie sehr unerwartet kam.
Mhm.
Okay, aber dann scheint es bisher noch nicht so ein
ja, ich hab das schon auch gehört, aber die Frage ist halt oft, man muss schon sehr genau hingucken, um zu sagen, was heißt das jetzt tatsächlich. Also viele Ergebnisse sind überraschend, aber es ist trotzdem sehr nischenmäßig und technisch. Ich habe mir das nicht genau angeguckt. Das klingt ja nach einem guten Seminarthema. Vielleicht. Vielleicht ist es auch so tief im Kaninchenbau, dass es schwierig wird. Dass wenig Leute darüber Seminar machen wollen? Oder dass es nicht zugänglich ist?
Müsste man auf jeden Fall das hier und eventuell noch das hypothetische Nachfolgemodul von dem
Das kann passieren, ja. Aber manchmal reicht es auch, wenn man in die Tiefe buddelt. Manchmal braucht man nur. Ja, die Namensgebung ist eh schon immer so ein bisschen quatschig. Aber gut. Alrighty, time to move on. And switch back to English too. So far we've talked about pseudo-polynomial, not pseudo-random. I'm already full in this one. We've talked about pseudo-polynomial algorithms, and we've talked about fixed parameter tractability. And by and large, these are the same, right? Pseudo-polynomiality is kind of a special case of a parameter, as we've seen, the max int. And all of those algorithms so far didn't compromise on what it means to solve a problem. And that's what we'll change next. The next unit starts I guess, second big part of the lecture, where we give up some of the correctness criterion for our algorithms and try to get further speed ups by doing so. This will keep us busy for a while, and in the first bit, we'll kind of set the stage mostly for the algorithms with a few examples and basically some terminology. So I'll give a little bit of motivation and maybe a deep dive in one specific topic just to make a point. Might keep us busy for today, and then we'll revisit a bit of the background. What's this about? Well, if we're faced with an hard optimization problem or an NP-hard decision problem, and all the known algorithms that we can think of still don't really help us in that they're still too slow, the only way forward seems to be to make compromises on what we want. Classical algorithms, as we've studied them in fixed parameter tractability, have to be always and exactly correct. And really think of exactly makes sense for optimization problems more than for decision problems. But really these are two separate properties, and we could give up either of them or both. And here we'll give up the first one, namely that the algorithms always work, or provably always work. And I guess the opposite of that is that they can occasionally fail. Now that sounds not too good, so we'll have to make sure that fail is in a specific way. For a deterministic algorithm, what fail means is that on some inputs it doesn't work. That's the only thing it could mean, because it has to do the same steps on the same input each time you run it. And that's maybe not so satisfying, because if your input is one of those that your algorithm fails on, you're still out of luck. So in a way, it's clear we have to do something that even if I give you the same input again, the next time you run the algorithm, something different will happen. And that's what we call non-determinism, because the algorithm is not deterministic, or the computation is not fully determined just by the algorithm and the input. On the other hand, I've marketed non-determinism when we discussed traditional complexity as something that's completely unrealistic and useless in practice, and just a hypothetical thing you can compete with. So we won't use general non-deterministic Turing machines here. But I think it's useful to think of randomization as a specific way of non-determinism, but one where you have control over how likely things are. And formally, it'll look quite different, but I think this is still the way to kind of see what fail means. We use random bits to guide the computation, so there's some assumed module of the machine that can generate randomness, and we won't discuss much what you can do there in practice. But this is both a solved problem and kind of not a problem, and a big problem, depending on what exactly you need. Getting some random bits is not that hard. You can measure the resistance of the voltage of some resistor. There's some randomness in there just from, at the end of the day, quantum physics, and you can calculate random bits from there, and they're true random bits for all that we know. On the other hand, if you have very specific requirements, and in particular if you need a lot of random bits in a short time, you might have to do something smarter. We'll come back a little bit on that, but for our computational model, mostly we'll just assume that there's some random bits. Now, the point of randomization is that instead of failing on some rare inputs that might still be the ones we care about, we rarely fail for any specific input. And by repeating, we can make it rarer. Okay. Why could this possibly be useful? Allowing something to fail, I mean, apart from making things worse, there's some somewhat distinct reasons why this can make life easier for designing algorithms. And we'll see examples of each, but maybe it's useful to already kind of distinguish them first. It often makes algorithms simpler. And simple is a complicated term. I'm currently program committee chair for a track of an algorithms conference that specifically invites simple algorithms or simple proofs of existing algorithms. It's actually a tricky problem. What does simple mean? It's in the eye of the beholder. But when you see examples, maybe you can agree that some are indeed simpler than the alternative that cannot use randomness. And intuitively for me, you can avoid dealing with the full generality of the problem by randomization. Often allows you to get away with the usual case. If you can get that to work, then randomization can sometimes do the rest. A totally different reason why randomization, and specifically this being correct most of the time but not strictly always, can help, is the idea of fingerprinting, or maybe checksums would be a better term. Fingerprinting kind of got stuck, but it's the wrong metaphor because from all I know, human fingerprints are actually unique or close to. You can identify an individual human being by the fingerprints. And this is totally not the idea of what fingerprints are used in computation or in algorithms. The idea is you take this complicated thing, the full human being, maybe the full genome, and you reduce it to something much simpler and smaller that's quicker to compare. That's the way the metaphor is to be taken. So instead of answering the full question, you answer a cheap surrogate question, but sometimes you have false positives. I mean, the other thing, this is also called hashing. Is the same. The implementation of fingerprinting usually is hashing. And that's what checksums also are in some form or another. So checksums, you would say, if you want to know if two files, long, big files are the same, you could compute some good checksum. And if the checksum's the same, chances are good the files are also the same. It's unlikely that there's a collision with different files giving the same checksums. That's a specific technique, but it's helpful so often that I made it a bullet of its own. And then the other reason is a bit more subtle. Maybe we'll see this today. Is sometimes you can prove lower bounds for algorithms by constructing an adversary that tries to make the algorithm fail by kind of modifying the inputs along the way. And by throwing in randomness in the algorithm, you make the algorithm itself less predictable. And so the adversary has less power. And that could mean that you can actually get stronger results. Typically, you can find faster algorithms or less costly algorithms using randomization. And you can prove any deterministic algorithm has to pay strictly more. There's another use case for randomization, which is also using randomized algorithms, but in a way has an entirely different goal of its own. And that's often called the probabilistic method. And this has virtually nothing to do with solving optimization problems and so on. Rather, you have some obscure object or object with certain properties where it's not obvious or not clear whether it should exist. And the idea is the proof technique says, okay, maybe you don't know. Let's try to design a randomized algorithm to construct such an object or to find such an object. And if you can prove that there's a positive non-zero probability that this algorithm succeeds, well, then there must be such an object. The trick here is that oftentimes this is much easier. There's various techniques. And it's non-constructive. It doesn't tell you how to exactly find this object or what it exactly looks like. It just proves that there is one. And because that's probably a bit abstract, I think Might be nice to have a specific example. And that was taken from Ramsey theories. Is kind of a whole area of specific discrete math results of this sort. Really, the gist of it is just this: you start with a complete graph on some number of vertices. And now I'm coloring the edges either red or blue. So every edge gets some color. And I'm doing this, I mean, this is very arbitrary. But every edge gets some color. And the claim is you can always find a clique of vertices that have all edges in the same color. Of size at least some bound that depends on n. And this is a lot of open problems connected to how exactly this R of n looks like, but I think you could take log n as a lower bound. I should have looked this up. So in my example, there's a triangle of the same color. For example, this red one. And I mean, if you think about this, of course, you can try to reason about this in various ways. But for graph of size 5, is it always possible to find a triangle of the same color? It's at least not obvious, right? It's not so clear. The idea of the probabilistic method would now be to say, let's design a randomized algorithm to find such an edge. And so I'm starting with the uncolored graph. I'm randomly coloring the edges. And then I'm trying to calculate the probability that my algorithm succeeds in finding such a monochromatic clique. And you can then reason over this algorithm a bit easier that, say, the expected number of such things it finds is strictly greater than 0, so there must be one. Okay, that the analysis uses things I'm going to introduce later, so I'm not going to do this now. But that's kind of the idea of what this probabilistic method looks like. And oftentimes, this is the only way we know to prove the existence of certain objects, which is pretty cool. On the other hand, it's also unsatisfying because it doesn't allow us to construct these objects. It just tells us that they exist. There's an obvious similarity between randomization and average case analysis. And this is really an undergraduate repetition that a good undergrad algorithms course will have drilled into you. But it's worth stating again just to make the distinction clear. Average case analysis can talk about deterministic or randomized algorithms, but let's suppose the algorithm is deterministic. So the same input leads to the same computation. I can still ask what happens for an average input. Randomized algorithms, the algorithm itself is not deterministic. It involves randomness and it generates the randomness. So it, even on the same input, does different computational steps. Average case analysis says, okay, the input is random and it's coming from some distribution. In randomized algorithms, our usual type of analyses, at least, will be worst case. We assume the input is the worst possible. But then we throw our random bits on it. And I guess it might be useful to say here explicitly that, because that term is also used sometimes, the adversary we imagine here is oblivious to our random bits. The person choosing the worst case input doesn't know what random bits we have. It's kind of logical because they're random, right? So how could they know them? But in theory, you could imagine that someone also can look at your random bits. And this is important to point out here. They cannot. At least they can't decide. They can choose the input based on the random bits. And then if we analyze things, the cost is given as an expected value if you do average case analysis, but the expectation is over the different types of inputs. If you do a randomized algorithm and worst case analysis, then the cost is also an expectation, but the expectation is over the random choices of the algorithm. So it's a different beast altogether, but the analysis techniques might still be very similar. Just because the randomized algorithm might effectively force the input to look like a random input. And so I guess here, one example would be a sorting algorithm might first shuffle the input to produce a clearly uniformly random permutation, and then it sorts. That's actually not a stupid idea in quicksort. Instead of picking random pivots in each step, you might, it's easier to program, at least, to first shuffle the entire list and then sort it afterwards. And then the sorting step can use standard choice of the pivot, maybe the first or last element, and nothing bad will happen most of the time. Okay. So just to make clear that these are very different in what they say. Sorry, it's super annoying that this is the wrong way around. Anyways. In the next section, I want to show you one concrete problem and make the point that randomization can indeed be more powerful than any deterministic algorithm. I wanted to show you one concrete example of this for one to make to show a concrete adversary, because I think this is insightful for other problems too, and also to drive home that point that randomization is really doing more than just making algorithms a bit simpler. So I'll try to avoid detailed discussion of what the randomization formally means. We'll come back to that. I should mention that this is not an NP-hard problem that we're working with here. And so also the randomization is not going to decide between exponential and polynomial or anything like this. The difference is smaller, but we can prove that it exists here. And the example is the selection problem, selection by rank, the thing that quick select solves. So just to recap, the input is an array of numbers or arbitrary objects that you can do pairwise comparisons on. And you're also given a number k, and you're trying to find the element that would be in that given position k if the array was sorted. That's a convenient way of saying that you want the kth smallest. It's a bit more specific or a bit more precise in case there are duplicates in the input. Then if you say the kth smallest, does that include duplicates? And what about all the elements that are equal to the kth smallest? You can avoid all that if you just say it's an element that could be in position k in the sorted list. Makes discussions here a bit easier. But for all that follows, you can assume that the numbers are distinct, and then it's really the same. Special cases that we'll focus on is for k is n half, then we're looking for the median element. So the element where half of the input is smaller and half of the input is larger. What you learned in undergrad is this quick select algorithm. Different ways to write it, but here's the one with a loop. You're maintaining a range of the array where you still have to work in. Initially, it's everything. And as long as that's not empty, you pick a random element from that range. You partition that range around that element. Everything smaller to the left, everything larger to the right. And then there's 3 different options. Sometimes you're lucky and the pivot element you picked is exactly the one that has rank k or is at position k in the end. Then you will eventually return it. Otherwise, if the splitting position where the pivot landed is too far to the right, then you have to continue searching on the left. K is still left of that. Then you adjust the upper bound, and the other one is symmetric. I suppose people remember what this works like. Really, the point here is if you don't do this random choice, the algorithm has a quadratic worst case, just as quick sort, the more famous cousin of this. And the other bit is the algorithm is really simple. It's simple to write down, it's simple to code, and it works really well. But it needs this randomization to be robust. Now you can show that it takes linear time in expectation, and you can compute much more about this, determine exactly how many comparisons it does, and so on. But let's not go there yet. Now, I also should mention that you can also solve the same problem deterministically. And the kind of algorithm you would have seen for that is the median of medians algorithm, where you group elements in columns of 5, sort those, then take the middle third, the third smallest of each 5, recursively find the median of that, and then partition with that guy. Substantially more complicated than this code for sure. Still very doable, but also much slower in practice if you compare the two. Okay, so far so good. So let's take a slightly closer look at what happens here and what we can do in the extreme cases, or in beyond these simple algorithms. All of what happens is within theta of n. We can do expected costs linear in n, and we can do deterministic cost linear in n, and there will be a lower bound linear in n. But the constant in front makes a difference here. So first of all, there's a lower bound for any deterministic algorithm, assuming it's comparison-based as for sorting. So a deterministic comparison-based algorithm for finding the median has to use roughly 2n comparisons in the worst case. Okay? That proof is a bit tricky. What I'll show you is a simpler version that gets a slightly weaker bound. Annoyingly, it's yeah, we'll see. So the same statement, just that now we have 1.5n comparisons. Or more precisely, we have n-1 and n-1 half. The reason why I split this up this weird way is that's what you get from the proof. And so let's design. Let's prove this. And there's essentially 2 parts. There's 2 types of comparisons. there's some comparisons which are necessary from an information theoretic perspective, which means if the algorithm doesn't learn about the outcome of these comparisons, it cannot be sure that the output it produces is correct. So in our case, we want to output some element x and claim that this is the median. So if I'm outputting this element x and claim this is the median, I, as the algorithm, I have to have proof of that. Otherwise, some mean person modifies the input in a way that makes my claim wrong. It's a bit like the typical argument in this direction. An adversary argument would be to find the minimum of n elements, you have to look at every element. Otherwise, if there's an element that you haven't even looked at, that you have not compared with anything else, then the adversary could make this much bigger or much smaller than the other elements, depending on what you claim the minimum is, and it will fool you. It will make your claim wrong. In the same way, you have to show that there's comparisons with the other elements, say n is 11, and the way we'll draw this is like a Hasse diagram for partial orders. So an element with an arrow down means this one is bigger than this one, and this one's bigger than this one. And it's a partial order, so this is transitive. But what I've shown you here is the certificate that x is a median. So the claim is, unless the algorithm has learned a partial order of this form, where your element x is in the middle, and there's some way to say these 5 elements are larger than x and these 5 elements are smaller than x, unless you have somehow learned the information of such a partial order, you cannot prove that your median is correct. If any of these edges is missing, I can modify the input so that your claim becomes wrong. Okay? If you think about it, what this was for sorting, you can also make the case, if you want to sort a bunch of elements, you have to learn which one's bigger than the others. So you have to arrange them in some linear order. That's the largest, second, smallest, blah, 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 down to the smallest. So for n elements, the certificate is just n-1 comparisons. But we know for sorting, we actually need many more comparisons. So the certificate comparisons are not always sufficient. And here as well, there's n-1 comparisons that you have to do to certify that the median is correct. But sometimes, and most of the times, you need extra comparisons to find the right certificate. And for sorting, we know this gap is really big. For medians, the second type of comparisons are non-essential comparisons. These are the ones where in hindsight, you know, I actually wouldn't have needed to do that comparison. If somehow someone would have told me what comparisons to make, I would not have done this one because it doesn't help me certify the median. So the thing is here, if I tell you this is the median, if I already give you that guess, and then you can compare that median to all the others, It's like one round of partitioning in quick select, and you immediately find that that's correct and that's the answer. Then you only need n-1 comparisons. What we'll try to prove is that in general, or in the worst case, it's not possible to make the correct guess without additional comparisons. In sorting, you do that lower bound with decision trees. There's just too many different things you have to determine, you have to distinguish. For the median, this wouldn't work. The number of different things is basically just n. There's n different choices for the median. And maybe you learn which ones are smaller, which ones are bigger, but you don't get this, this big gap for an n log n. So how can we still do, against deterministic algorithms, some bound on non-essential comparisons? So a non-essential comparison is one that's not part of the certificate. So in particular, any comparison that compares an element that's at the end strictly larger than the median to another one that's strictly smaller than the median, it doesn't help us find the median. Okay? The L and S are these sets, so let's define M as the true median. L is all the elements that are larger than the median. Likewise, the smaller ones. And by the way, we know that these are of the same size, right? But that's it's not needed here. So any element from L and any element from S, if I compare those two, I kind of, at the end, I already know the one in L will be bigger than the one in S. So that comparison is wasted. But what we'll play now is adversary. We're given some fixed deterministic algorithm that will do its thing, but it can only access the elements via pairwise comparisons. So at some point, the algorithm has to pick two elements and ask which one of those is larger. And at this point, we jump up as the adversary and will construct the input comparison by comparison, trying to fool the algorithm to do as much work as we can make it do. That's the general pattern that adversaries against some algorithm always take. They always have this kind of form. In the specific case here, what we do is we maintain the elements of the input in three sets. Two will be S and L, where we've committed that this element will eventually be smaller than the median. So you should think about it this way. We initially have the n elements lying around, and they're just uncolored marbles. And we can decide what they are ordered like. But we don't have to fix that choice until the algorithm asks us about specific comparisons. We can change our mind along the way if we feel like it. We just can't make it a lie what we've told the algorithm in the past. We have to stay consistent to the previous answers. So initially, every element will be in U, undecided. We don't know yet, or we haven't committed yet to that element being eventually smaller or larger than the median. And so now, whenever the algorithm asks a comparison, asks a question, which of the two is smaller, we check if we've already decided where the elements are. So the algorithm asks us, is x less than y? Now we check if x and y are not in the same sets. Then we answer according to the small 1 elements are all larger than the undecided ones, and these are all smaller than the large ones. Okay, that decides the comparison, and that's all we do. If the elements are both in S or both in L, then it doesn't matter. We just answer something according to an arbitrary order of these elements that we somehow fix. You could say by the time they entered this set. And the last option that still is possible is that they are both in U. Okay. In this case, we say arbitrarily that one is smaller, one is larger. And now we put x in the small set and y into the large set. And what have we done with this step? Well, we've generated a non-essential comparison. Because at the end of the day, neither x nor L will be the median, and they will lie on opposite sides of the median. So this comparison that the algorithm has just done is turned into a non-essential one by the way we answered. Okay? And so that's all we do. How expensive is this for the algorithm? We always need the n-1 certificate comparisons. The algorithm has to learn those, no matter what it does. That's this part. And for the remainder, because every element starts initially in U, and we only move elements when we do this last step, for the algorithm to learn about the true median, well, we only reveal the median really at the very end if there's a single element left in U. And this is kind of automatic by the first case. As long as there are elements in, if the algorithm is stupid enough to do comparisons where both elements are in S or in L, then it pays more, and we don't even charge it for that. But it has to get all the elements out of U to make progress. because we're never going to reveal useful information to it before that. The useful information only comes from the first case. So it has to get all the elements out of U, all but the true median. And so it's n-1 elements that have to go. But for each step, we take 2 of them, put them away. So it's n-1 half that we get as comparisons. Right? With each comparison that we generate, 2 elements are moved away from U. So we create 1 comparison for A. So against this adversary, any deterministic algorithm will have to pay the certificate comparisons and at least n-1 half additional comparisons, which we turned into non-essential ones, but the algorithm couldn't have known. It's out of luck. This proves the 1.5n. There's a sequence of works that improves that bound up to the 2n, which is where it currently stands. Whereas the best upper bound is 2.95n, and it's unknown how many comparisons you really need for deterministically finding the median. It's kind of unsatisfying that we don't know this simple question. What I wanted to say is how to get the higher lower bounds is by making this adversary more sophisticated. Here we immediately put x and y from the unknown sets, 1 up, 1 down, and we harvest 1 comparison. The generalized forms of that keep some order within U, unless that compares only a few elements. You can keep them around and then do a lot of case distinctions on what the adversary should do, and you can make the algorithm pay a few extra comparisons. But that gets super technical, and I think it's worth doing once, but not digesting in a lecture. The key idea is these kind of reasonings of maintaining the elements in some sets and choosing when to answer what. I wanted to go through this proof because I think it makes blatant obvious that if the algorithm is randomized, a lot of this trickery is harder to do. It's you can't really force the algorithm to make the same kind of now I'm struggling because this lower bound is also true for randomized algorithms. And I think this specific construction, there's nothing that stops you from doing that against randomized algorithms. The more sophisticated algorithms that maintain this partial order, they make this harder. But you can at least see from this proof that designing an adversary might be easier if the algorithm has to commit to a fixed sequence of comparisons up front. The last bit to drive home is randomized algorithms. The one we've seen, quick select, it doesn't actually beat this bound. In expectation, you need 3.39n with quick select. But that's just because the algorithm is kind of wasteful and simple. You can do better. And I don't want to discuss the algorithm in too much detail because that leads us too far into analysis. The key idea is to take a large random sample from your array. And the rough size of the sample is this n to the 2/3. That's a big sample, but it's a little O of n, right? So with this sample, you can do a lot. In particular, you could actually just sort it and make the algorithm simpler. It's a bit more efficient to recursively select from this. The idea is that you suppose you want to find the median. So here's your k. You pick a large sample from this array and find two elements whose ranks are just left and right of k by a small amount. And then you do one big partitioning step to narrow down the list to this tiny space. The partitioning costs 1.5 n comparisons because you're doing it with two pivots. You compare every element to one of the pivots and those that are larger to the other one. And so because these are so close together, it's essentially half of the elements that you have to pay a second comparison for. So it's 1.5 on average. And then you can work out that all the rest in the algorithm is little o of n work because you're working on a small sample or you're working on cases that are unlikely to occur. What this needs is knowledge from statistics about how likely is it that this estimator for the median that we get from the sample is off by so and so much. As I don't want to get into this in detail. But the bottom line is that you can do randomized median finding in 1.5 n comparisons. And that's strictly less than the lower bound we've seen cited, the 2n comparisons that you need deterministically. Okay. So at least in terms of this constant factor of the number of comparisons, randomization gives you strictly more power. And here, I guess you can see it as you take away power from the adversary to make you pay extra comparisons by hiding your next steps. Okay, that was a bit of a little detour deep dive in one concrete problem where you can work out this separation. What we want to come back to next time is what happens on NP-hard problems. Can we get more dramatic improvements from randomization there? And for that, I want to first define things properly. There's a few interesting things from just the mathematical side that happen that I think is worth setting straight first. Okay. Enough for today. See you tomorrow, guys. Or see you later at the tutorials, but see you tomorrow for the next lectures.